All right, we're going to take a little closer look at the conditions under which you can be sure that the waves are going to add together and make constructive interference. For example, loud sound, bright light, tall water waves, versus conditions when the wave sources are going to conspire to make either quietness, smooth water, or darkness if it's light waves, okay? So first let's look at the case of what's called constructive interference, where where again you get loudness or tall water waves or bright light, right? So the idea here is, again, we're looking at interference between two wave sources, and so here's one wave source and another wave source, and I happen to just pick this location in space. I could have picked other places around, and what we're trying to do is learn, why it would be at a certain place, why you would have loud sound or quiet sound, okay? So, so we're going to begin with the case of what's called constructive interference, where it's going to be like loud. So the key thing to look at here is something called a path difference, okay? So what you do is you look at the first one of the wave sources. So here's source one, and here is what is going to be called path one, this distance. So we'll call this path one. Well, how far is path one? One way to measure how far it is to see how many wavelengths fit in there. Okay, so we happen to be like at a peak right now, the way that I drew this. So if you just kind of count peaks, it goes 1, 2, 3. So this, I happen to choose a point where this wave happens to be peaking like right now at this point. So the distance here is 3 wavelengths. Just be careful how you count. Don't start with 1 here, because right, like when you're born, you're not 1. You got to wait a year. So right, 1, 2, 3. So path 1 is 3 wavelengths long. Okay. So now let's look at the other path. Of course, it's so creative. I'm going to call this one path 2. So here's path 2. Right, and if we just play the same game here, so here's path 2. And path 2, you can tell, is 1, 2, 3. I made it exactly 4 wavelengths. So path 2 equals 4 lambda. Right. Now what's happening at this instant, right at this instant, the peaks are arriving at this instant. But if we wait just a little bit after this, this valley will move to that point, and this valley will move to that point. So the valleys will also arrive at the same time. So being loud is not just about peaks arriving, but you also need, say, the valleys to arrive at the same time. So the waves are doing the same thing at the same time at this place, okay? One thing to notice about this is if I were to move this speaker closer up to here, so that this was 3 and that was 3, they would also be arriving in phase, and it would continue to be loud, okay? So we'll come back to that point in a second. So what's key here is you notice the path, what's called the path difference. This is the most important thing on this whole unit, honestly. So the path difference, which I'm going to call delta path, okay? And it's really just path 2 minus path 1. Okay, the path difference is how much farther did one wave have to go than the other. That's the most plain English way to say it. Well, also path 2 minus path 1 is going to be 4 lambda minus 3 lambda. So it turns out it's just 1 lambda. So the path difference is exactly 1 wavelength, and it's going to be loud. Okay, so for loud sound. Now the thing to imagine here is, suppose I could move this speaker. Well, if I kept the speaker kind of like on an arc around here, and I kept it always 4 lambda from this point, it would continue to be loud if I swung it around in an arc, because all that really matters is this path difference, okay? So it's helpful if you can imagine other places where it would be loud, right? So we kind of mentioned, or I hinted that if you just slid this thing up 1 full wavelength, that would be loud. Notice I could, right, if it was here, then the path difference would be 0, because this one would go 3 and that would go 3. Okay, so 0 wavelengths also seems to work, okay? Another thing you might imagine is if I just move this one back exactly 1 wavelength, where this one was going 5 and that one was going 3. So, and then that would give a path difference of 2 wavelengths. So ultimately what we lead up to is if the path difference is either 0, 1 wavelength, 2 wavelengths, 3 wavelengths. So the way to capture this in general is delta path equals n lambda, where this guy can be 0, 1, 2, 3, or anything else that's an integer like that. This is very important. This is then the condition, so it's worth a box and some stars. This is for constructive interference. So what's key is the path difference. So something I didn't draw here because it would be like slightly harder to draw, but say if it would have been the case that this were 3.25 and this were 4.25, it would still be loud because the difference between 4.25 and 3.25 would be 1. So if the path difference is an integer number of wavelengths, it's going to be loud. Now when kids see this, they're usually like, well, how do I know which one it is? The answer is it's all of them. At locations that have a path difference of 0, at all those locations, it's loud. At locations that have a path difference of 1 wavelength, it's also loud. So that's something to keep in mind with this. All right. So let's just quickly look at the case of the other case where you actually have destructive interference. Okay, where you can ensure that the waves are going to perfectly cancel each other. So if you look at the picture below, we're going to play the exact same game. Okay. This top wave, this top path is 1, 2, 3 lambda again. So we can say path 1 equals 3 lambda, okay? Now you notice this bottom path, well let's count. Here you start at 0 and then you go 1, 2, 3, and then you can see that we do a half cycle, okay? So this path here is, path 2 is going to be 3.5 wavelengths. 3.5 lambda. Okay, so the key here is since this one has gone the extra half wavelength, this wave is like valleying while this one is peaking. Okay, and so these guys are going to conspire to punch each other out, right? Then a short time later, when the peak of this bottom wave arrives, that's right when the valley of the top wave will arrive. So what's going to happen is if your eardrum was here, these waves are going to conspire to make the air pressure stay flat, okay? The air pressure is not going to wiggle between high and low because every time this wave, the bottom wave wants it to be high, the top wave wants it to be low and vice versa. Okay, so it's going to be dead quiet there, okay? And so what you can see here is your path difference. So here your delta path, which again is path 2 minus path 1. So I'm going to try to stop writing so messy. In fact, I'm going to fix that for quality control here. Let's redo that a little better. Delta path, which is path 2 minus path 1. Okay. You can see that that's going to be 3.5 lambda minus 3 lambda. So that's exactly half a wavelength, 0.5 lambda. Right? That is going to give you a quiet sound, okay, or destructive interference. Quiet. Now, just like we did before, you might imagine that, well, if I moved this up exactly a wavelength, then this would be 2.5 and that would be 3. The difference would still be half a wavelength. So it's still going to be quiet. So if I moved this up exactly a wavelength, it'd be dead quiet. I can also go back so that this would be 4.5 and that would be 3. Then the difference is 1.5. That's also going to be quiet. And so in all its glory, then, we can generalize this to all the places where it's going to be quiet. So it would be like, if the path difference is half a wavelength, 1.5, 2.5, 3.5. So one convenient way to write that is you can say delta path equals, well, I'm going to write it 2 ways. One way to do it is you can say if the delta path is half a wavelength, or 3.5 wavelengths, or 5 half wavelengths, comma, dot, dot, dot. The way that this tends to be written, I don't know, maybe more concisely, is like this. You say delta path is n plus 1/2 lambda, where again, and then the n retains the same meaning as it had up above, where it can basically be any integer. 0, 1, 2, comma, dot, dot, dot. All right, see if you plug it in. N equals 0, you get that one. N equals 1, you get that one. And it builds them all up. This is also worthy of a box and some stars, because this is the condition for destructive interference or quiet sound. So very, very important. Most important thing in this unit, okay? or destructive interference. Again, kids might get hung up on, well, how do I know which one it is? It's not which one, it's all of them. All of them. There are a whole bunch of places where you could put the speaker to conspire to make it quiet at that place. Now, what we did was looked at the extremes. There are places where you can completely cancel the sound, and there's places where they perfectly add together. There's a whole continuum in between there. Like you could have it where it almost cancels. So for example, if the path difference was, instead of getting exactly 0.5 wavelengths, if we got 0.498 wavelengths, then it would like almost cancel, right? It would, then it would be like pretty quiet there, but it wouldn't quite cancel out. So what we did was we fixated on the extremes, okay? Final point I want to make, I can't stress enough the importance of what path difference is. I'm going to actually hassle you guys about this a lot to make sure you have it. The most plain English definition of path difference I can think of, okay, so which we're going to call delta path, and I'm going to bother to write it down here. It is how much farther one wave has to go than the other. That's what the path difference is. One wave must go than the other. So if you ever want to know if you have two sources of waves, whether it's going to be bright or dark or in between, or loud or quiet or in between, what you want to do is focus on this path difference. That concept is key. You find one path, you find the other, you take the difference. If it's an integer number of wavelengths, it's going to be loud or bright. If it's a 1/2, 3/2, 5/2 number of wavelengths, then you're going to have perfect cancellation of the waves. So really, really important page for this unit.